In this video, I'll be going through my notes on Level 2 waves. A link to the PDF and a list of corrections are in the video description. Light. Light is an electromagnetic wave, which means it is made up of fluctuating magnetic and electric fields. How light behaves depends mainly on its wavelength. We categorize light into 7 wavelength-dependent groups: radio waves such as radar and AM and FM, microwaves used in Wi-Fi, Bluetooth and microwave ovens, infrared used by your TV remote to send signals, visible light, ultraviolet used in sterilization and curing resin, X-rays which are used in imaging and radiotherapy, and gamma rays which are used in PET scanning or positron emission tomography. Light travels at 300 million meters per second, or 3 times 10 to the 8. Unlike sound, it does not require a medium to travel through. Reflection basics. Waves reflect symmetrically, or put mathematically, the angle of incidence equals the angle of reflection, or that theta I is equal to theta r. So if we have an incident ray striking a surface at a particular angle theta I to the normal line, our reflected ray is going to leave at an equal angle theta r. I have here a high-powered green laser reflecting off a plane mirror and a fog machine so we can better see the beam. As you can see, the beam reflects symmetrically, or in other words, the angle of incidence equals the angle of reflection. Nature of images. We describe the nature of images formed by lenses and mirrors in 3 ways. So if we consider an object, our image size could be either diminished, the same size, or enlarged. The orientation can be either upright or inverted. And we can also say whether the image is real or virtual. A real image can be projected onto a screen, and the rays actually meet. For a virtual image, the rays do not meet, but do appear to. Don't stress too much about understanding this now. We'll be revisiting it in a number of pages. Curved mirrors. Concave mirrors converge rays. Convex mirrors diverge rays. Parabolic mirrors focus rays to a single point. Spherical mirrors approximately do. Ray diagrams. We use ray diagrams to model how mirrors and lenses produce images. Consider a mirror, in this case concave. We have what we call a principal axis, along which is our focal point and our center of curvature, where the center of curvature is double the distance of the focal point. We have an image from our principal axis, and we can draw a number of rays to determine the location of our image. Mirror diagrams. Rays are drawn from the object tip and converge at the image tip. Ray 1 goes through or towards the focal, then parallel to the axis. Ray 2 is the opposite, parallel to the axis, then through or towards the focal. And Ray 3 is just symmetrically through the middle. For a convex mirror, we have our ray through or towards the focal, which is on the other side over here. It then strikes the mirror and reflects parallel to the axis. Ray 2 goes parallel to the axis, and then through or towards the focal. Ray 3 just reflects symmetrically through the middle. Now as you can see, all 3 of these rays are diverging. So they don't converge in real space, but they do appear to converge in what we call virtual space. So if we backtrace each of these reflections, we can locate a convergence, which is the position of our virtual image. With convex mirrors, the image is always virtual, upright, and diminished. For a concave mirror, the nature of the image depends on where the object is in relation to the focal point. For this example, we'll consider an object outside the focal point. Our first ray goes through or towards the focal, and then parallel to the axis. Our second ray goes parallel to the axis, then through the focal. And our third ray is symmetrically about the middle, giving us a real convergence and the location of our image. So for an object outside the focal, our image is real and inverted. If it's at the focal, our rays will be parallel, meaning that they don't converge and no image will be formed. If the object is inside the focal, we will see a virtual upright and enlarged image. Here I have a blank piece of paper and a large concave mirror. The mirror is positioned facing a pair of windows. As I move the paper in front of the mirror, we observe an image of the windows. The image is real because we're able to project it and inverted because it's upside down. This is an illusion disk. It consists of a base, a lower concave mirror, an object to observe, and an upper concave mirror with a hole in it. Assembling this together and viewing at the right angle, we're presented with an optical illusion, a holographic image floating above our object. Visualizing this with a diagram, we can imagine light from a point on our object reflecting off our top mirror, and then the bottom, and then finally traveling through our top hole and converging on the other side. Descartes' method. Consider the following situation where we have a mirror, a focal length, an object at a particular distance with a particular height, and likewise an image. Descartes' method gives us a way to mathematically relate these. 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. For this equation, it matters whether or not things are positive or negative. The focal length is positive when the mirror is concave, since the focal point is in front of the mirror. It's negative for a convex mirror, because the focal point is behind the mirror. When our image distance is positive, our rays actually meet and we have a real image. When it's negative, our rays only appear to meet and we have a virtual image. Magnification. We define the magnification of an image as the image height as a fraction of the object height, or the image distance as a fraction of the object distance. As an equation, our magnification is the image height divided by the object height, or the image distance divided by the object distance. If our magnification is greater than 1, our image is enlarged. If it's less than 1, our image is diminished. Newton's method. Whereas Descartes' method uses distances from the mirror, Newton's method uses distances from the focal point. So if we once again have our mirror and our focal point at a particular distance, we have an object at a distance from the focal point SO and an image at a distance from the focal point SI. We can relate these mathematically as the object focal distance multiplied by the image focal distance is equal to the focal length squared. Negative numbers have no meaning in the above equation, so to determine the nature of the image, a ray diagram can be drawn. Refraction. When light enters a different medium and changes speed, it also changes direction. We call this refraction. So if we consider an incident ray at an angle θ1 to the normal, entering a different medium and refracting to form a refracted ray at an angle θ2 to the normal. We can describe our mediums as N1 and N2, where N1 and N2 are the refractive indices of each medium. A refractive index is just the speed of light in a vacuum divided by the speed of light in the medium. In other words, the higher the refractive index, the slower light travels. We can put these all together mathematically using Snell's law, which states that N1 sin θ1 is equal to N2 sin θ2, which we can also use to get this relationship here. N1 over N2 is equal to V2 over V1, lambda 2 over lambda 1, or sin θ2 over sin θ1. I have here a beaker of water and a packet of water beads. Left overnight, the beads absorb a considerable amount of water and now have a refractive index very close to the water itself. Submersed in water, the refractive indices between the balls and the water is very slight, resulting in a minimal deflection of light. To the unsuspecting eye, this makes the balls all but invisible. Total internal reflection. When a ray moves from a slow medium to a fast medium, it bends away from the normal. This means that for a particular incident angle, called the critical angle, the ray refracts along the boundary. Increasing the incident angle above this causes the refracted ray to disappear. We call this total internal reflection. So for the situation where our incident angle is less than the critical, where we have our ray starting off in N1 and then entering the medium N2, we are always going to see some amount of reflection, and in this case we're also going to see some refraction at a particular angle θ2. This is the situation we've been looking at so far, except we've been ignoring the reflection. If we increase our incident angle to be equal to the critical angle, we're going to see our ray refract along the boundary, or in other words, our refracted angle is going to be 90 degrees. This is the situation that we described right here. If we then increase our incident angle so that it is greater than the critical angle, we have our incident ray and our reflected ray, but we have no refracted ray. This is the situation that we described in this paragraph. Now, it's worth reinforcing that this only occurs when you move from a slow medium to a fast medium. The reason is, this requires the ray to be bending away from the normal, where this is of course our normal, and our ray is bending away from it. Since when θ1 equals θc, our refracted angle θ2 equals 90 degrees, or in other words, this situation here, we can use Snell's law to write n1 sine θc equals n2 sine 90 degrees, where we are writing θc instead of θ1 since they are equal, and we're writing 90 degrees instead of θ2 because they are equal. Bearing in mind that sine of 90 degrees is equal to 1, this term effectively cancels out, leaving us to divide both sides by n1 to get sine θc equals n2 over n1, and then taking the inverse sine of both sides to get θc equals the inverse sine of n2 over n1. In the exam you will not be given this equation, you will instead be expected to derive it. I have here a very strong laser and a glass prism. Turning off the lights and shining the ray at the prism, we see the ray totally internally reflect at our two glass-to-air interfaces. Because these interfaces are at 90 degrees, we see the ray exit in more or less the same direction that it entered. I have here a green laser and a section of plastic tube. Dimming the lights and shining the laser through the tube, we see the light appear to flow through the tube and emerge on the other end. This happens because the optical properties of the tube are such that the light totally internally reflects at every air-tube interface. Apparent depth. When a submerged object is viewed from above the water surface, it appears at a shallower depth than it is. So if we have a crab beneath the water, light is going to reflect off our crab and travel towards the surface. The light rays speed up as they exit the water, causing them to bend away from the normal, where it strikes our eyes. Two eyes are required to perceive depth. The image is perceived to be where the rays meet, and so unaware of a change in direction, our eyes assume that the light has travelled in a straight line, right back to here. So as you can see, we perceive the image of the crab in a different location to the object. Dispersion. In practice, the refractive index of a material is dependent on wavelength. This causes shorter wavelengths to refract at greater angles than larger. Put simply, violet refracts more violently. This is iconically demonstrated when white light strikes a prism in a particular way, producing a rainbow. As you can see, we have our shorter wavelengths refracting at a larger angle than our larger wavelengths. It should be noted that this is the opposite relationship to diffraction. Lenses. Lenses are transparent objects that are curved to either converge or diverge rays. A convex lens is a converging lens, and a concave lens is a diverging lens. Lens diagrams. As with mirror diagrams, we can use ray diagrams to describe images from lenses too. The rules are mostly the same. Ray 1 is through or towards the focal, and then refracts parallel. Ray 2 goes straight through the middle, and ray 3 goes parallel, and then refracts through or from the focal. For a concave lens, our ray 1 goes towards the focal, specifically our focal over here, and then refracts parallel. Ray 2 goes straight through the middle, and ray 3 goes parallel and then refracts from the focal, specifically this focal here. Now, if you get confused as to what focal you should be using, an easy way to check is by considering the type of lens. Because this is a concave lens, our rays should be diverging. So our 3 rays here should be spreading apart. If they're not, then you've probably chosen the wrong focal somewhere. Now, because these rays are diverging, we're going to have a virtual focal point, which we can find by backtracing our 3 rays, giving us the location of our image here. And it should be noted that concave lenses always produce upright diminished virtual images. For a convex lens, ray 1 goes through the focal and then refracts parallel, ray 2 goes straight through the middle, and ray 3 starts parallel and then refracts through the focal. The intersection gives us the location of our image. Now, similar to a concave mirror, the nature of the image for a convex lens depends on where the object is in relation to the focal. An object outside the focal will produce an image that is real and inverted. At the focal, no image will be produced as the lines will be parallel and won't converge. An object inside the focal will produce a virtual upright enlarged image. Here I have a pair of brightly lit windows and a convex lens. Moving the lens in front of a piece of paper, we see an image come into focus. The image is real because we're able to project it, diminished because it's smaller than the real windows, and inverted because it's upside down. Lens equations. As with mirrors, both Descartes and Newton's equations can be used with lenses. Recalling Descartes' equation, our magnification equation, where a positive focal length is used for a concave lens and a negative for a convex. A positive image distance means the image is real as the rays converge, and a negative image distance means the image is virtual as the rays only appear to converge. Recalling Newton's equation, where the image focal and object focal distances are taken from the same side focal. So the object's focal distance is taken from the focal point on the object's side, and the image's focal distance is taken from the focal on the image's side. Wave motion. A wave is a propagating disturbance. They cause a relocation of energy, but not matter. Water and sound waves are mechanical waves, which require a medium to travel through. Light or electromagnetic waves do not. We can classify waves as either transverse or longitudinal. Transverse waves, such as water and light, oscillate at 90 degrees to their direction of travel. So if our wave is traveling towards the right, we see it oscillating at 90 degrees up and down. Half the height of our wave is our amplitude A, where we have our peaks at the top and our troughs at the bottom, and our wavelength is the distance between one wave cycle. Longitudinal waves, such as sound, oscillate in the direction of travel. So if our wave is once again traveling towards the right, our longitudinal wave is just a series of compressions and expansions, meaning that the particles are oscillating in the direction of travel. Once again, our distance for one wave cycle, or peak to peak, is the wavelength lambda. Period is the amount of seconds per wave, or the time taken for a complete wave cycle. For moving waves, it is the time for a complete wavelength to pass a fixed point. Frequency is the waves per second, or the amount of wave cycles per second. For moving waves, it is the amount of waves passing a fixed point per second. Period and frequency are mathematical reciprocals, meaning that we can write frequency is 1 over period and period is 1 over frequency. Wave graphs. Here we're going to look at two types of graphs showing wave displacement. Wave displacement versus time plots our wave displacement against time, where our peak-to-peak difference gives us the time between peaks, which is, of course, the period. Plotting wave displacement versus distance. In this case, our peak-to-peak measurement gives us the distance between peaks, or in other words, the wavelength. I have here a tuning fork and an oscilloscope connected to a microphone. When I strike the fork, we see a clear waveform on the oscilloscope. Our time per division is set to 0.5, meaning that each square represents 0.5 milliseconds. Our wave goes up and down in roughly 5 squares. Multiplying that by 0.5 gives us a rough period of 2.5 milliseconds. This gives us a frequency of roughly 400 Hz, which for a rough estimate is pretty close to our actual frequency of 426.6. Sound. Sound waves are propagating waves of compression and expansion. They require a medium to travel through. Although it is a longitudinal wave, it is often represented as a transverse pressure wave, where we see our longitudinal wave, our areas of high pressure are our peaks, and our areas of low pressure are our troughs. The frequency, aka pitch, is inversely proportional to wavelength. Therefore, as one increases, the other decreases. So if we have a large wavelength, we have a small frequency, and if we have a small wavelength, we have a large frequency. Sound tends to travel faster in denser materials. This is a music box. It makes music by rotating a metal drum, upon which are indentations, which strike tines of different length. The shorter the tine, the higher the frequency. This makes sense considering the equation V equals F lambda, where we keep the material the same and therefore the wave speed. A shorter tine means a decreased wavelength, and therefore an increased frequency. Currently the music is quiet because the vibrations are only being produced by this small metal frame. By placing the frame on a larger surface, we're able to vibrate a larger volume of air, resulting in a significantly increased volume. Wave speed. Wave speed can be written as the distance divided by the duration. We can also define wave speed as the time taken or period for a complete wavelength to pass a fixed point, or that the velocity is the wavelength divided by the period. Substituting our period is equal to 1 over frequency, we can also write this. Wavefront reflection. Wavefront diagrams are used to depict waves in 2 dimensions. Lines represent peaks. When drawing reflecting wavefronts, first draw the ray, then draw the wavefronts perpendicular. So if we have a barrier for our wavefronts to reflect off, we could first draw our incident ray and then our reflected ray, and then draw in our perpendicular wavefronts. Diffraction. When waves move past a boundary, they bend around it. Larger wavelengths bend more than short. We call this behavior diffraction. So in each of these cases we have a barrier, and we see our longer wavelength bends around more than does our shorter wavelength, meaning that with a longer wavelength we have more diffraction than we have with a shorter wavelength. Plane wavefronts passing through a gap diffract to form radial wavefronts. So if we imagine plane incoming waves passing through a small gap, we're going to see those wavefronts spread out into radial patterns. For this relatively small gap, we're going to observe more diffraction than we would for a larger gap. Wavefront refraction. When drawing wavefront refraction, I suggest the following steps. First, draw your incident ray. Then, draw your incident wavefronts. Next, draw your refracted ray. And then, draw your refracted wavefronts. In this case, we have gone from a fast medium to a slow medium. This results in our ray bending away from the normal, and as you might note, this produces an increased wavelength. Phase. Phase is a way of comparing different points in a wave cycle. A complete wave cycle is 360 degrees, or 2 pi. Phase difference on a wave. A and B are quarter of a wave out of phase, which is 90 degrees. A and C are half a wave out of phase, so 180 degrees. A and D 3/4, so 270. B and D is half, so 180. B and F is 2 full waves, so 720. And C and E is 1 complete wave, or 360. Phase difference between waves. Waves lined up are in phase. Shifting our blue wave by a quarter of a wavelength brings them 90 degrees out of phase. Shifting it by half a wavelength means it is now 180 degrees out of phase. Pulses at ends. Let's consider a pulse moving towards a fixed end. A fixed end means that this point does not move. The situation afterwards is a reflected pulse that is also inverted. This inversion occurs because the wave applies an upwards force to the fixed point, and the point responds by exerting an equal opposite downwards force to the wave, inverting it. Let's now consider a loose end. A loose end means this point is able to move freely, such as a loop around a pole. Our situation afterwards is much the same as earlier, except now the reflection is upright. This happens because the end is free to move, and as it does, it generates an upright wave in the opposite direction. Pulses at boundaries. Consider a pulse moving from a fast medium to a slow medium, such as a thin rope to a thick rope. In our situation afterwards, we are going to have an inverted reflection, inverted because the boundary behaves like a partial fixed end. We're also going to have some of that pulse transmitted, and as the transmitted pulse travels slower, its wavelength is shorter. We can show this with our v equals f lambda if we have a reduction in velocity, and our frequency is the same as it always is in these interactions. Our wavelength must decrease, and the amplitudes are less as they sum to the original. For a pulse moving from a slow medium to a fast medium, so the reverse situation to before, the situation afterwards is going to have a reflected pulse, where the reflection is upright as the boundary behaves partially like a loose end. And we're also going to have part of our pulse transmitted, where the wavelength is longer, via the same reasoning here, except the situation is reversed for an increased velocity. And once again, the amplitudes are less as they sum to the original. Superposition. When a wave occupies the same position as another wave, their amplitudes add together. So if we have a wave of +1 amplitude and +2 amplitude, the resulting amplitude is going to be +3. And if we had the same situation but with a negative amplitude, we'd end up with a -3 amplitude. When waves combine and form a larger wave, we call this constructive interference, of which these are two examples. If we had a -1 amplitude and then added on a +2 amplitude, -1 + 2 gives us +1. If we had a +1 amplitude and a -1 amplitude, +1 - 1 is 0, giving us complete cancellation. When waves combine and form a smaller wave, or cancel out, we call this destructive interference, which we've seen here. Standing waves. When identical waves traveling in opposite directions overlap, they produce stationary points of constructive and destructive interference. This can happen when we have two separate sources, but this can also occur when a single wave is reflected back on itself. And so if we imagine our resulting amplitude at one moment in time, and then half a wave cycle later, we see our pink nodes of destructive interference, where peaks meet troughs, the waves are meeting 180 degrees out of phase, resulting in complete cancellation, meaning that at these points here, we're going to see no movement. At our blue antinodes, we have constructive interference, where peaks meet peaks and troughs meet troughs, so our waves are meeting in phase, and we get a combined amplitude. And so at our antinodal points, we have our maximum movement. 2D interference patterns. When two wave sources are adjacent, they produce an interference pattern. The order number n is the wavelength path difference between the sources. Consider our two sources down here emitting our waves. We have our antinodal lines, which are lines of constructive interference. Peaks meet peaks and troughs meet troughs. Amplitudes add to their new amplitude, and our order number is a whole number. Our central antinodal line is n equals 0, n equals 1 on either side of that, n equals 2 on either side of that, and so on. Our nodal lines are lines of destructive interference, where peaks meet troughs, the amplitudes cancel, and our n is something 0.5. Our first nodal lines are 0.5 either side of our 0, and then 1.5, 2.5, and so on. Now to analyze this a bit further, if we were to analyze this point here, we can see we have two wavefronts intersecting, meaning that we have a peak meeting a peak, meaning that we have an antinodal line, which as we can see, we do. If we were to instead consider this point here, we have two wavefronts here and two wavefronts here. Our indicated point is halfway between these two pairs of wavefronts, meaning that it's where a trough is meeting a trough, meaning that we have an antinodal line, which we of course do. If we instead consider this point here, we see that we have a wavefront from one of our sources intersecting with halfway between the wavefronts of our other source, meaning that we have a peak meeting a trough and therefore a nodal line. Path difference. Path difference is the difference in the distance between a selected point and each of the sources. It is usually expressed as a multiple of the wavelength. For example, 2 lambda, 7.2 lambda, or 3.5 lambda. Where the path difference is a whole number of wavelengths, there is an antinodal line. Where the path difference is something 0.5 wavelengths, there is a nodal line. So in our example here, we have 2 sources. For our yellow point, we can count 1, 2, 3, 4, 5, 6, 7 wavefronts. From that, we can subtract 1, 2, 3, 4.5 wavefronts, which gives us a path difference of 3.5 wavelengths. Because our path difference is something 0.5, we have a nodal line. For our green point, we can count 1 wavelength, from which we subtract 1, 2, 3 wavelengths, which gives us a path difference of 2 wavelengths. Because our path difference is a whole number, we have an antinodal line. For our aqua point, we can count 1, 2, 3, 4, 5, 6, 7 wavelengths, from which we can subtract 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 wavelengths, which gives us a path difference of 3 wavelengths. Because our path difference is a whole number, we have an antinodal line.